So let's take a closer look at proof. And we're going to break it down. First, we're going to take a look at the forms of some theorems, and then we're going to step through direct proof and indirect proof. Indirect proof comes in a couple different formats, and we'll look at proof by contrapositive and proof by contradiction. So what does it mean to be a proof? First of all, a common type of proof is an informal proof. In mathematics, and the first time something is shown to be true, we tend to use a real formality. But oftentimes, it's appropriate to use informal proof. An informal proof is a type of proof that might use more than one rule of inference uh, in one step of the proof. So from one line to the next, you might apply multiple rules of inference. Steps might be skipped. So when it's obvious and unnecessary to specify, steps could be skipped. And the rules of inference are not always explicitly stated. It's easier sometimes to understand and to explain to other people, but there's a cost because it's also easier to introduce errors. And the applications of proof, the ways that we use this information, it's really important to get this piece right. So it comes out in verification of computer programs. So making sure that the code that we're creating is legitimate and it's doing what we expect. If we take in a set of premises as input or information, then we're going to output or return a conclusion that follows logically. They're used to establish that operating systems, which we all rely on so heavily, are secure, which we, of course, hope to assume. They also enable programs to make inferences in artificial intelligence. So taking in new and different information and applying the rules of inference to learn something new, and showing that system specifications are consistent. So what do the forms of theorems look like? Well, the forms of theorems can be many. There are several theorems that come in the following format. For all x, P of x implies Q of x, and they can look like many things. Have something. All even numbers are divisible by 2. Anytime you hear that all in the space, or if you talk about something across a domain, all students, all rational numbers, you pick a domain. Once you apply it, generalize something to the whole of the domain, then you have something probably of this form. So we typically do this by letting there be an arbitrary element of the domain and assuming that antecedent is true, showing the consequent must follow. And then by universal generalization, the truth of that original formula for all x, P of x implies Q of x follows. So if it's true for an arbitrary element of the domain, then it's true for all elements of the domain because that arbitrary element was not specific, right? It was any element within the domain. And so generally what that means is this all boils down to proving something of the form P implies Q, right? If our standard approach to solve for all x, P of x implies Q of x, what we're really doing is saying, assume this one thing is true and show that another follows.